Good afternoon, I'm Jesse Serrano and I go to Binaries High School.
Good afternoon, my name is Rayana Yassin and I'm from Binaries High School.
I'm David Chow, I'm from Mountain View High School.
I'm Mike Aguiniga and I'm from Carson High School.
Our project surrounds the topic of high mass X-ray binaries. But before we get into high mass X-ray binaries, we have to talk about high mass stars. So what are high mass stars? High mass stars are stars with at least or around 8 times the mass of our sun. They are bigger stars than lower mass stars, so they burn their fuel quickly, that being the hydrogen in their core. They are responsible for fusing heavy elements as in heavy metals and gases. So after their supernova, they spread these elements throughout the universe and onto different planets. So what are high mass X-ray binaries? Well, a binary between 2 stars is when 2 stars orbit around a common center of mass. So I would imagine that as a giant cosmic seesaw where these 2 stars are on both sides, and the middle is closer to the star with the bigger mass to try to keep the balance. And after one of these stars supernovas and turns into a compact object, that's when the binary actually gets interesting. So, massive stellar evolution. Massive stellar evolution is what I would say is like a timeline in which a star takes, right? So the first stage would be the main sequence, which is kind of like the adulthood of a star. A high mass star would spend at least 90% of its lifespan in its main sequence, and these stars burn their fuel relatively quickly, so after that they would get their red supergiant phase where they start to run out of energy in their core, and they start to expand. They look bigger and brighter, but they're actually not as strong as they used to be. But when fusion in their core stops in general, they compact, they're more susceptible to the gravity keeping their shape, and it collapses and explodes, causing a supernova. The remains of a supernova can be one of 2 compact objects, being a black hole or a neutron star. Black holes are extremely rare because it takes an extremely mass star in order to capture light after its explosion. And a neutron star is its most common path after a supernova, which is just a compacted ball of neutrons and electrons. It might look extremely small, but it actually has an extremely high density. So why are high mass X-ray binaries important? Well, high mass X-ray binaries are extremely important because they're extremely rare in nature. So it's important to understand what happens during these binaries. How does this binary affect the stars in said binary? And how exactly are these binaries different from lower mass stars binaries? So how do we get our data? Well, it could take millions of years for a binary to even form, so it's important to use simulations. We use Poseidon, which stands for Population Synthesis with Detailed Binary Evolution Simulations. So the way this simulation works is you put in basic data, as in separation, orbital periods, and the mass of the stars. And then it gives you high detail data, and we use that in our presentation. So throughout our presentation, we're aiming to answer these questions. How do high mass X-ray binaries form? Are there different formation channels for black holes versus neutron stars in high mass X-ray binaries? And are different evolutionary paths more common than others in these binaries?
Now we're going to move on to the neutron star paths, but before we start the simulation, I want to clarify some of the units. The mass of a star is how many times bigger that star is compared to the sun. So in this example, it will be 7.77 times greater than the sun. The orbital period is represented in days, and the separation is represented in astronomical units, which is the distance between the Earth and the sun. So in this example, it is 37.3 times the distance between the Earth and the sun.
So right now we're going to look at Poseidon neutron star high mass X-ray binary path 1. These phases take millions of years, and the simulation starts off with ZAMS, or zero age main sequence. And this particular zero age main sequence leads star 1 to supernova, which then leads it to the end of the simulation where it becomes a neutron star with a high mass companion star. And then path 2, this ZAMS leads us to star 1 also supernovaing once again, and also coming to the end of the simulation, but this time with a high mass companion star that's decreasing at the end. And this is the rarest path that we found. This ZAMS leads star 1 to also supernova again, as we see over there in the picture of the supernova. This is where it became the rarest of them all, where we have only found one because of a Roche lobe overflow by star 2. It's basically when star 2 starts to absorb mass from star 1, and the simulation comes to an end with a neutron star and a high mass companion star. We've calculated all the ratios of the masses of stars, which is you take the mass of star 1 divided by the mass of star 2, and you get the ratios between the stars. And the paths all follow a similar orbital period and separations with their own paths, such as path 1 just continues to increase, while path 2 increases and decreases and increases once again, and then path 3 increases and then decreases and then increases and then decreases at the end of the simulation.
So the other end a high mass star can undergo is becoming a black hole. So out of all our simulations, the first path of a black hole follows the 0-age main sequence, which is the adult phase of the star. So as you can see, compared to the neutron stars, the black hole masses are way bigger. So you have your 2 stars, and then star 1 undergoes a supernova and turns into a black hole, while star 2 remains the same. And after millions of years, the simulation ends. And this was the most common path. The second most common path, path 2, is similar to path 1. So you have your 0-age main sequence, the adult phase of the stars. Star 1 explodes into a supernova and becomes a black hole. Now, what's unique to path 2 is something called the Roche lobe overflow. So mass from star 2 is actually being sucked into the first star, and that's why you can see that its mass went from 21 to 18.8, and after millions of years, the simulation ends. So the third path was our rarest path out of all of our simulations, and it is similar to path 2 in that it undergoes ZAM's 0-age main sequence. Star 1 explodes into a supernova. There's Roche lobe overflow, so mass from star 2 being accreted into the black hole that star 1 became. But what is unique is something called a common envelope, which is a phenomenon where the 2 stars are enshrouded into the envelope of one of the stars. So as you can see, they're both together within the same envelope. And after that, the simulation ends. So some observations we made with the black holes are that the masses have to be really, really massive for them to become black holes. As you can see, the mass ratios for path 1, we have 1.9, which was the most common. Path 2, we have the second most common, which is 2.2, and the rarest, path 3, with a mass ratio of 1. Some observations we made are that the orbital period will get larger as the masses of the star get smaller, and so will the separation, because as the stars are getting smaller, they're also being pushed farther apart.
So to summarize, you have learned what a high-mass X-ray binary is and its importance. You have learned that the high-mass star can become a neutron star or a black hole, and you have learned that Poseidon is a useful tool to find out the paths that high-mass X-ray binaries can go on, whether this star becomes a neutron star or a black hole. Now, in the neutron star paths, you can see that the masses are all different, and that the separation and orbital period has a trend, whether it is increasing or decreasing. There's a relationship between the mass ratio and the separation/orbital period, because once a star loses mass, there is greater separation between the 2 stars, and it will take longer for them to orbit each other. Now, there are some distinctions in the black hole path, mainly that the orbital period is more extreme, as well as the mass ratio. The separation fluctuates a lot more in this path as well. And in the black hole paths, the common envelope phase was more present.
So had we been given more time to work on this project, we would have loved to find out if there are different high-mass X-ray binary evolutionary pathways. So what other channels exist for the high-mass stars to take? We would have loved to decipher different factors and initial conditions such as mass and orbital period that can influence the path the star takes. And we would have loved to look at the interaction between the objects in the binary, so whether they're exchanging mass, and things like that. We'd like to thank Dr. Lazzarini and our lab mentor and our teacher mentor, Ani Mosmanian, for all your help and for being just really amazing during this project. Any questions?
I'd like to know if you know in your studies how these black holes and how these supernovas, and when they explode, how does it affect space, or does it affect the Earth at all?
Okay. So actually, all the materials and like elements that we have on Earth came from a supernova at some point because of the elements being spread around the universe, right? So they're different planets are given gases and metals and other elements. And it affects the universe as, yeah, it just gives materials to different planets. Yeah. Oh, also during supernova, there's gas formations that form other stars. So it gives birth to massive, like a lot of other stars.
Thank you.
Did you experience any challenges during this research project?
I would say definitely. There is, online it's extremely hard to learn, so there was a steep learning curve, but I think we all really pulled together and we were really great at communicating. And even when one of us couldn't like make it right on time to the in-person week, we still communicated and at least tried to get everybody involved. And the practices just got easier later on. At first it was extremely hard to talk to new people. I didn't know these people before this, but I can say that they're extremely important friends to me now, and I just love learning beside them.